Now in the last video we started talking about Markov chains and how the outcome of one event will determine the outcome of the next event. I guess it leads us to the question of, will you ever reach a situation where your transition matrix will eventually produce a result that will never change? You'll have a constant outcome. And that's what we're going to investigate. If we can arrive at that, we've arrived at what's called a steady state matrix. So have a look at the scenario here. Let's once again just talk about share market, perhaps like we did last video. So this one's set up like, so if the share market were to rise today, 0.5 of a chance it rises tomorrow, 0.2 of a chance that it stays unchanged, 0.3 of a chance that it will fall. If there's no change in the market today, 0.1 of a chance that it rises tomorrow, 0.4 of a chance no change, 0.5 of a chance that it falls, and of course if it falls today, there's the three probabilities. Now, to work with a steady state matrix, you can't actually start with a specific known event, because if we said that the state matrix right now was, we knew that it was definitely rising today, and applied the transition matrix over and over and over again, all you would end up here is with just the first row of the transition matrix. And we actually don't want that. So what we're going to do is come up with a scenario where we're not 100% sure what it's doing today. There could be a chance that it's rising, could be a chance that it's not changing, could be a chance that it's falling. And we're going to start with something where we have three non-zero values. So let me set that up and we'll come back and show you what to do next. Now let's make the assumption that the chance of the stock market moving or not moving today is given by this state matrix. So today is a 0.3 of a chance that it could go up, 0.4 of a chance that it could remain unchanged, and 0.3 of a chance it could go down. Now, if I were to apply the transition matrix to that over and over and over and over again, would these three numbers eventually arrive at values that will never change? Obviously, if I applied that matrix to it once, I'm going to have three different values here. Apply it a second time, I'll have three different values again and again and again. Will it eventually hone into this value heading towards a constant figure, this one to a constant figure, and this one to a constant figure? Well, the answer is yes, and let's see how we do that. Now, if we were to investigate this transition matrix, that's really all we need to play around with. We don't really need to touch the state matrix. If I just take my transition matrix and just raise it to some particularly high power, try 10 and then try 11. If you get the same answer both times, you've reached steady state. I'm actually going to investigate what happens if I raise my transition matrix to the power of 20. And if you were to plug this into your calculator, and I suggest you do it now, plug this into your calculator, raise it to the power of 20. While you're doing that, I'll write up the answer that I get and see if you get the same with your calculator. Now, did you arrive at that when you raise p to the power of 20? Well, we have, what you're looking for is, if I have all my rows giving exactly the same values, that's a surefire indicator that I've probably reached a steady state matrix. You should probably do a couple of things to check that though. If I raised p now to the power of 21, I should get the same result. And if you did that, you would find that that is indeed what you get. Very good. Now, with the steady state matrix, technically what we're looking for is this scenario. We're looking for a situation where I have my state, whatever it happens to be. If this is actually this matrix, if it is actually the steady state matrix, I should be able to multiply it by my transition matrix and produce no change. I should end up back at the steady state matrix. So we can check that. Let's actually apply this. What I'm suggesting is the steady state matrix is going to be, I'm suggesting that the steady state matrix is actually going to be any one of these rows. So 0.3, 0.3, 0.4. Regardless of the initial state that I started with, 0.3 of a chance, 0.4, 0.3 in that order, by applying this matrix over and over and over again, these three numbers will eventually settle down to these three numbers. If that's the case, I should be able to take this matrix, x, 0.3, 0.3, 0.4, and now multiply it by the transition matrix, and I should get that result. Grab your calculator out and try that. Type this matrix in, multiply it just the once by transition matrix P, and see that you don't get that particular result. And that means this is our steady state matrix. It means our initial matrix eventually transformed by our transition matrix over and over again eventually produces a steady state that will never change. And the best way to find that is just take your transition matrix and raise it to progressively higher and higher powers until you get a situation where all rows are the same, and as you then increase the index by 1, you get exactly the same result. And then go and do a check. Take the steady state matrix that you think you've got, times it by your transition matrix to see that you end up with exactly what you started with. It is a bit complex, a little bit confusing, but as you try some of these problems over and over again, you'll begin to get the hang of what steady state matrix is all about. So best of luck with them.